In this video, we are looking at velocity time graphs. Hopefully you've already seen the video on distance time graphs. One of the things that you need to be really clear about is that velocity time graphs are different. One thing they've got in common is that the time runs along the horizontal axis, but apart from that, you really need to think carefully. For example, on a distance time graph, we saw that flat sections of the graph correspond to the person or the object being completely still. That's not true anymore, as we'll see when we go through this example. Lando is testing his go-kart's top speed. He accelerates until his speed stops increasing, so it stops going up. Then he maintains the top speed for a while, and then he brakes to a standstill, as shown in this graph. One of the first things we need to do is make sure we understand what velocity means. The velocity is simply the speed in a given direction. You can see that these units for velocity, meters per second, are the same as the units you might use for speed. However, they are not exactly the same thing. The direction really is important when it comes to velocity. For example, think about two cars travelling on the motorway at 70 miles per hour, but they're travelling in opposite directions. They would have the same speed, they're both doing 70 miles per hour, but they would not have the same velocity. In fact, we could say that one of the cars has a velocity of 70 miles per hour in that particular direction, and the other car then would have a velocity in the same direction of negative 70 miles per hour because it's actually travelling the opposite way. Now, in this example, we don't have to worry about any negative velocities. So for the purpose of this, we can just assume that the velocity means speed. The next word we need to know is accelerate. Now, someone who is accelerating is changing their velocity. So if they're getting faster, they are increasing their velocity and therefore they are accelerating. If they are getting slower, they're still changing their velocity, so getting slower would also be called acceleration in maths. If we had a positive velocity, then we would say a negative acceleration would make them slower. So just be aware of that. In everyday English, of course, we wouldn't really talk about negative acceleration. If they were getting slower, we would actually say that they were decelerating. Finally, we need to know what the word standstill means. Braking to a standstill just means braking to a complete stop, so the speed has to be 0 when you're at a standstill. Now, let's just take a look at this graph carefully before we read the questions. You'll spot that we've got a line that's increasing, then we've got a flat part of this graph, and then we've got a line that's decreasing. Now, you might remember on a distance time graph, a flat part meant that a person or object was staying still. They weren't moving, they weren't changing their distance. However, on a velocity time graph, that's not true anymore. This flat part actually means that they're not changing their velocity, or in this case, they're not changing their speed. This person is staying at 20 meters per second. And in fact, this is the top speed. So a flat part doesn't mean that they're standing still at all. It just means that their speed is being maintained. Similarly, on a distance time graph, to find the speed of an object or a person, you would have to find the gradient of the line on the graph. To find the speed on a velocity time graph, it's actually much easier. For example, if we want to know how fast the person was travelling 18 seconds after setting off, we could look up 18 on the graph and then read across. Remember, the vertical axis here is the velocity or the speed, and 18 seconds after setting off, this person is travelling at 10 meters per second. So finding a velocity or speed is easy from a velocity time graph. You just read up and across. You don't need to find the gradient of these lines. In fact, if you did find the gradient, what you would be working out is the acceleration, but we're not going to go into that in this video. Let's have a look at the questions then. The first question says, what is Lando's top speed? So we're looking for the highest points on this graph, and that is up here. He reaches a top speed of 20 meters per second. The second question asks how long it takes him to reach the top speed. Well, he first gets to that speed 10 seconds after setting off. So the answer is 10 seconds. The next question asks us, how long does Lando drive at the top speed? Well, he starts driving at the top speed 10 seconds after setting off, so he has accelerated all the way up to that point for the first 10 seconds, and then he's at his top speed and he stays at his top speed of 20 meters per second all the way along this flat bit here, and that ends at this point, which is 16 seconds after he set off. So he started off at top speed here at 10 seconds and he finished 16 seconds after setting off. So he was at top speed for a total of 6 seconds. That's the difference between 10 and 16. So what we've established so far is that he spent the first 10 seconds accelerating, getting faster, the next 6 seconds at its top speed, which is what it tells us in the question, and what happens next is that he brakes to a standstill. And that's what's being asked in this question. How long does it take Lando to slow down from the top speed to a standstill? So from this top speed, he has to slow down to a standstill. That is a speed of 0 or a velocity of 0. So down here. Well, he gets to a standstill 20 seconds after setting off, and he started slowing down 16 seconds after setting off. What we're looking for is this particular amount of time, and that is 4 seconds. That's the difference between 20 and 16. So 16 seconds after setting off, he slams on the brakes and he slows down until 20 seconds after he set off. That's 4 seconds after slamming the brakes. He ends up completely stopped. The last question is asking us how far Lando travels during the time he is at top speed. So he is at top speed, we saw, for 6 seconds. And during that time, he's travelling at the top speed of 20 meters per second. So he does 20 meters per second for 6 seconds. 20 meters per second means he's doing 20 meters every second. And if he does that for 6 seconds, he's going to travel a total of 20 times 6, which is 120 meters. Now there's one more thing that I'd like you to spot, and that's going to come in useful in a future video. The distance he travels, the 120 meters, between these two times, 10 and 16 seconds, happens to be the area under this graph between those two times. So from 10 to 16 seconds, what we're dealing with is actually this rectangle. This rectangle in green has an area of 120 because we can see that this rectangle has a width of 6. The units in this case are seconds. Remember, this here is a 10. And the height of this rectangle is 20. That's this here. And the units in that case were 20 meters per second. The point is the area is 20 times 6. Exactly what we've worked out here. So the area under a velocity time graph gives you the distance travelled. We're going to see that in a later lesson.